Hello and welcome everyone to part 4 of the section 8.3 notes. We're going to cover page 58. So here we see we have what looks like a geometric series here. We have a quantity raised to the n power, and we're going to keep adding that together. You'll notice that it's a little bit different. We're starting with n equals 0 and then going to infinity. I actually want to make a remark about this. So for geometric series, they typically come in two flavors. And so there's the one that we commonly know, where it's the sum n equals 1 to infinity, a times r to the n minus 1. But also, they can start at n equals 0, and the only difference is that the power of the common ratio is no longer n minus 1, it's just n. And so you could have done all the problems on the previous page by finding an expression starting with n equals 0 and then going from there, and then leaving the power as just n. But I typically prefer to teach it this way and then just add this on as an addendum. And the reason that you can leave the power at n when you're starting at n equals 0 is look what happens. When n equals 1, what is the first power of r with this exponent n minus 1? Well, it's 0, right? And so really, there is no quote-unquote difference between these two things that we're looking at here, because you're always starting with a times r to the 0. It's just that you're starting with a different n value. And so what that means is that you have to modify the exponent of r. This is what's known as re-indexing. It's not going to play a big role here for us, but this is, like when you look at something like this, is what I'm trying to say, is that this is like a valid geometric series because it's of this type. And so what we see is that the sum n equals 0 to infinity of x to the n, well, in this case, a is 1, I think. And so this right here, absolute value of x less than 1, that's just another way of saying that x is strictly between minus 1 and 1, right? If x is in this range, then its absolute value has to be less than 1 and vice versa. And so this is a over 1 minus, and now r is just x, right? And so you can see how we're, eventually what we're going to be getting to is what are known as power series, where your common ratio will be allowed to be different. And what that means is you're going to introduce a variable, right? And so this is our first sort of example of what's known as a power series. And you see that this is a function. So what you can do is, I don't know if we'll have time to get to it because of Corona and everything like that, but we're going to have essentially, there are ways to express functions as power series, right? So this is a function and this is a power series. But in order for this function to equal that power series, we needed the absolute value of x to be strictly less than 1. All right, that's just an aside that hopefully we'll have time to come back to. All right, now, the next two series we're going to introduce, the first one is what's known as a telescoping series, and then the second one, and then we'll conclude this video, is what's known as a harmonic series, the harmonic series, possibly the most important series that you'll learn, next to like a geometric series. All right, but telescoping series first. So what we're going to do is we're actually going to do this one from first principles, because you'll notice that it's not geometric, right? There is not something being raised to the n power, which you keep adding, right? So this is not geometric. And another dead giveaway that a telescoping series is maybe the right thing to do is we see that the bottom can be factored nicely. Notice the denominator is n times quantity n plus 1. And so what that means we're going to do is first we are going to find the partial fraction decomposition of 1 over n times n plus 1. So 1 over n plus 1. Well, these are both linear factors, and so we need to write this as a over n plus b over n plus 1. And we can recombine into a single fraction with common denominator n plus 1. It looks like a gets multiplied by the n plus 1, and b gets multiplied by the n. I mean, go ahead and finish this on your own if you like, but it looks like what we're going to get is that a plus b has to be 0, since that's the coefficient of n, and then a is just a constant coefficient, so a is 1, right? Because it has to equal this one here. Since there's no n here, a plus b, the coefficient of n has to be 0. So b is then -1. Okay, so in reality now, this sum right here, so let's give ourselves a little more room. This sum right here can be rewritten as the sum n equals 1 to infinity. And now I have to put in parentheses the partial fraction decomposition. So a is 1 and b is -1. And you could call this minus. You could just pull the minus right here if you like, but that's up to you. All right, so what we're going to do is we're going to do this from first principles. So let's start with S1. Remember, S1 means plug in n equals 1, and that's it. So I get 1 over 1, okay, 1 over 1, plus -1 over 2. Now S2, well, that's plug in n equals 1 plus plug in n equals 2. So it's really just going to be the last Sn that you got, and then plug in the next integer. So 1 over 2 plus -1 over 3, right? And ooh, you notice I can simplify this. Notice this is actually just 1 minus 1/3, and this one I'm going to write as 1 minus 1/2. All right, let's find S3. Let's see here. So we get 1 over 1 plus -1 over 2 plus 1 over 2 plus -1 over 3. And now I plug in n equals 3 into this. So I get 1 over 3 plus -1 over 4. And you'll notice some more simplifying here. This is 1 minus 1 over 4. So if you were a betting person, what do you think Sn is going to be? Well, S1 is 1 minus 1/2. S2, 1 minus 1/3. S3, 1 minus 1/4. So I would bet something like that, right? It looks like I'm always getting 1 minus 1 over, and then whatever n value I'm at, whatever my subscript is, but then plus 1, right? And you'll notice I didn't actually combine, like simplify these fractions, because I'm trying to get a handle on what the partial sums look like. And it might be a little unruly if you start adding them all together. Like this is 1/2, 2/3, 3/4. I mean, maybe you can get a handle on it, but for more complicated examples, it's easier to just leave it like this, right? Okay, well remember, if the limit of these partial sums converges, then we say that the infinite series converges, and it would converge to that value. Well, what is the limit of these SNs? Well, 1 doesn't change, and as n becomes large, 1 over n plus 1 moves to 0. So it looks like this limits to 1 minus 0, which is just 1, right? So since this converges, since the limit of the partial sums converges, then the infinite series also converges, and so we would say that that is equal to 1. So hence the sum n equals 1 to infinity, 1 over n plus 1 equals 1. Done. And you might be wondering why it's called a telescoping series. Well, look here. As I start to compute the partial sums, you'll notice that I write out the long form and then it condenses. So think of like a, I don't know, like what you'd see in like Pirates of the Caribbean or something, like an old-timey telescope that sailors would use, how it pulls out and then retracts, you know, as you want to use it. So it's like we write it all out and then it actually contracts down to something much more simple. So that's where the name telescoping comes from. All right, harmonic series. Put a star next to this one. This is a very important example. You'll notice that the things I'm adding up 1 over n's, right? So I plug in n equals 1, I get 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, etc. Okay, let's determine if this converges or diverges. So we're going to use first principles. And once we've concluded whether or not the harmonic series converges or diverges, you don't need to re-go through this process. You can just use the fact that it either converges or diverges. So let's find out. So what's S1? Well, plug in n equals 1 and that's it, right? So it's just 1. Nothing too crazy going on there. All right, S2. Well, it's 1 plus 1/2, right? You take the old value and then add to it, plug in the next integer. All right, now I'm going to do something a little cheeky here. I'm going to skip S3 and go straight to S4. Well, S4 is the sum of the first 4 numbers, so starting with n equals 1 plus 1, so I get 1 plus 1/2 plus 1/3 plus 1/4, right? And now, here's a neat observation. This is actually bigger than, well, what if I took this 1/3 here and replaced it by 1/4? It's not clear why I'm doing that, but just bear with me. Then the number I get over here, 1 plus 1/2 plus 1/4 plus 1/4, is a smaller number than having that 1/3 there, right? I've taken 1/3 and replaced it by something smaller, so the thing on this expression on the left is bigger. That's why the caret, the absolute value symbol goes this way, right? All right, well, this is 1 plus 1/2 plus 1/2, which I'm going to write as 1 plus 2 over 2. Now I'm going to skip, so I guess there were some dots here. I skipped S3. I'm going to skip down to S8. So this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, right? And now the 1/3 I'm going to replace by a 1/4, and then these 3 guys right here, the 1/5, 1/6, 1/7, I'm going to replace by 1/8. Again, it's not clear why I'm doing this. So please just bear with me here. I think we're going to be getting to the punchline soon enough. And so let's see. I get 1 plus 1/2. Now notice this is another 1/2, these two 1/4 added together. And now these 4 1/8 are also a 1/2 themselves. So I have 1, 2, 3 1/2, also known as, and then plus that leading 1 there. So this is 1 plus 3 halves, right? Okay. If you were a betting person, what would you say the next number I would skip, like S sub what would be the next number? Well, I went 1, 2, 4, 8, 16 maybe, right? And I'm not going to write all this out. I don't have room to write 16 terms, but it would go 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9, you know, etc., etc. But I think what you're going to find is that it's going to be bigger than 1 plus, well, following this process, how many halves do you think I'm going to have? Well, probably 4, right? Since it was like 1 plus 1/2, it was here, 1 plus 2 halves was here, 1 plus 3 halves, 1 plus 4 halves is probably the next. Then I would skip maybe all the way to S32, and that would be bigger than 1 plus 5 halves. Okay, so in general, well, what am I getting here? Well, this is 2 to the first, this is 2 to the second, 2 to the third, 2 to the fourth. Oh, and 1 is 2 to the 0, right? So technically this is 1 plus 0 halves, right? So it looks like when my subscript is 2 to the n, I'm going to get a value that's bigger than 1 plus n halves, right? 1 plus n over 2. And now you notice, well, my powers of 2, well, those go on forever, right? So I'm always going to find numbers bigger than 1 plus n over 2. And so what I have found is some of these Sn values, in particular the ones where the n value is a power of 2, is always bigger than 1 plus n over 2. And 1 plus n over 2 I know goes to infinity, right? So let's actually remark that. Since the limit n goes to infinity, 1 plus n over 2 is infinite, then the limit as n goes to infinity of these particular Sn values, the ones where the number is 2 to the power of 2, that's also infinity. Well, I mean, the punchline is then that we have found some parts of the sequence of partial sums that diverge to infinity, and so the whole sequence of partial sums Sn must also diverge to positive infinity. And so the harmonic series is actually divergent, right? So write this down, like seriously, highlight it, do whatever you need. But it is a very important example of a divergent series, and we'll explore that a little more in the next video.